Hello everyone. So today we are going to carry out the experiment on the spring, and we have this one, the compression spring, and this is the tension spring, and the attachment is as such that both the springs are there in one single machine, and the moment we apply the load, at the same time both the springs will undergo some deflection, okay, because the load will be applied on both the springs. This is the attachment is such that this spring will undergo compression and this spring will undergo tension. Okay. So as we know that we have a formula, and in this particular test we have to carry out the modulus of rigidity of the material of the spring. Okay. Remember, we have to carry out the modulus of rigidity of the material of the spring. First we'll we'll see the complete procedure, how to calculate the modulus of rigidity of the spring material for this compression spring, and the entire procedure is same, and we have to carry out the same experiment for this tension spring. Okay. So the things which are different is in this particular compression machine, the number of turns will be different from this one. The diameter of this specimen, this spring, will be different from this one. The external diameter of this spring will be different obviously because this is a bigger one, okay, and this is smaller one. The number of turns is more in this one, the number of turns is lesser in this compression spring. Okay, so let us talk on this one first. Okay, and what is the formula which is involved in this, we will discuss after discussing the complete procedure. Okay, so this is the machine. Okay, and this is, you can see this is the release valve. Okay, if you release it like this, now this is the unloading position, means whatever load you have applied in this one, if you move means rotate it in the anti-clockwise direction, it means that you are releasing it. Okay, and before applying the load, what you have to do, you have to rotate it in the clockwise direction, and up to some extent what will happen, that after some extent it will fix. Okay, you'll find that it is fixed now. Now this is the moment, then means this time you can apply the load. Okay, and this lever you can see. Okay, by this you have to apply the load. Okay, and this is a machine where the hydraulic load we have to apply. It's not the, it's not the electrically operated machine. We have to apply the load hydraulically. Okay, so this is the lever. Now we have fixed it. We'll move it like this. Okay, now the load is being applied, and the applied load you can see from this dial. Okay, the moment you press it, you will see the deflection in this dial. Just now I'll show you. See, we are applying the load. See, the dial is moving. This needle is moving. It is showing the load applied. Okay. Now, as of now, we have applied 0.5 kilonewton load. Here you can see one division is equal to 0.1 kilonewton. It has been written here, and there we have applied till up to, I think, 4 or 5 division. So whatever, if it is 4 then it is 0.4 kilonewton, if it is 5 then it is 0.5 kilonewton. And see, you can see this is one division, means sorry, 1 kilonewton, then 2, then 4, then 6. Okay, so from 0 to 2, one more bigger division is there. It's not written 1, but that is 1 actually. So before that one, the middle one is 5. So it is exactly at 5 actually. Okay, fine. So from this dial we will see the load applied. Okay, and from this extensiometer we will find the deflection. Okay, here we will find the deflection. You can see, as we know that as we are applying the hydraulic load from the bottom, so this disc will go upward, and as this disc will move upward, the compressive load will get applied here. Okay, the compressive load will be applied here, and this needle will show us the extension, or you can call it as the deflection. Okay, initially it was at 0, and when we applied the load of 0.5 kilonewton, it came at I think it is at 15 m, sorry, it is at 15 mm nearly, okay, 15 or 14, whatever, you'll see while performing the experiment. So in this particular experiment, what we'll do, that we will apply the load in 5 different parts, okay. First we'll apply the load of 0.5 kilonewton, then 1, then 1.5, then 2, then 2.5, okay. And we will measure these 5 extensometer readings, that what is the extension and for what is the deflection at load P is equals to 0.5, then what is the load at P, what is the deflection at P equal to 1, what is the deflection at P equal to 1.5, and so on, okay. And after this we'll put all the values in our formula, and we'll find the 5 different values of the modulus of rigidity, okay. One value, for example N1 for load is 0.5 and deflection 1, okay. Then N2 for another load and another corresponding deflection, N3 for third load and third deflection. So this is how we will find 5 different values for the modulus of rigidity, and we'll take the average of all those 5, okay. And another some of the things which we require is the diameter of this particular spring material, okay. And we can see that it is the cylindrical one. So with the help of this vernier caliper, okay, we can easily find the diameter, okay. Just we have to keep it, okay, exactly like this. So I'm not showing that how much diameter is coming, whatever comes you have to take it, okay. So with the help of this vernier caliper we will find the diameter of this spring material, okay, and we will take the radius in our consideration, okay. So this is the diameter of the material, then the diameter of the spring we have to measure, so, and that will be the external diameter. So this is how we will measure it, like this, okay. This is the right, this will be the diameter of this spring, the outer diameter, okay. And again we'll take the outer radius, okay. And one more thing we will take, that is the number of turns. The number of turns means 1 turn, 2, 3, 4, 5, 6, 7, and one more turn is there which is inside, which is inside. So total 1, 2, 3, 4, 5, 6, 7, 8. 8 number of turns are there. Then now we'll see the formula and we'll discuss that how we'll calculate the modulus of rigidity for this spring, okay. So here, as we can see that as of now we have applied the load of 1.5 kilonewton, okay. 1.5 kilonewton is the load applied, and this is the extensometer reading, okay. Whatever it comes, it's nearly 35 mm, okay. 35 or 34 mm is the extensometer reading. So what I told you that we will take 5 different readings at 5 different loads. What are those readings? Readings of the extensometer readings, the deflection. So 5 different deflection at 5 different loads we will take, okay. So this is at the time of applying the load, okay. And again we will take the same readings, okay, means the deflection at the time of releasing the load. For example, the 5th load is 2.5, okay. So the deflection at 2.5 will be same both the times, and again we will release this lever, okay. As I'll show you, I'll release, the moment I'll release it will come down. Now again I'll fix. Now this is again came back to 1 kilonewton, okay. Now at 1 kilonewton again we'll take the reading. So this is called as the reading in the reverse loading case, okay. This is known as the reading, the deflection reading in the reverse loading case. And again we'll remove it, we'll release this valve, and the moment it come at 5 we'll stop it, at 0.5 we'll stop it, and again we'll take the reading, okay. So means we will take 5 different deflection reading in the direction when we apply the load, and again we will take 5 different readings when we release the load, okay. And then we will take the average of those readings, means For example, if the reading is coming 14, okay, the deflection 2 is coming 14 mm, for example, in the application process, okay, in the application of the load, and the same deflection 2 is coming 16 in the releasing process, okay, while releasing the load. So we'll take the average of those two. 14 plus 16, that is equal to 30 by 2 is 15. So 15 will be the deflection 2. So this is how we have to carry out. Now we will discuss the formula, okay.
Yes.
So here we have the formula, which is N, the modulus of rigidity of this spring, is equal to 64 R cube W into small n divided by del is delta is deflection into d raised to the power 4. The unit will be Newton per mm square. Okay. Now 64 is the constant. R, capital R, is actually the radius of the spring, which is equal to d, capital D by 2. Okay. Now this W is the load which we are applying. This N is the number of turns. This delta is the deflection which we measured. Okay. Those are the deflection readings, and this d, small d, is the actually the diameter of the spring wire, or the diameter of the spring material. So remember all these things. Okay. Now see, first we'll calculate n1, and as I told you that we have taken 5 different readings. So if I make some some table, so it will be like this: serial number, then load, then reading. Reading will be this deflection reading at the time of loading, and again reading at the time of deloading. Okay. Then after that, modulus of rigidity. Okay. So in this case, for example, at serial number 1, we will put the load 0.5 kilonewton. 2, it is 1 kN. 3, 1.5, then 2, then the last one is 2.5 kilonewton. So these 5 are the different values of loading. Then reading, for example, we got, for example, I'm talking, it is 14. Okay, and then it came, let us suppose 22, then it came, let us suppose 31, it came suppose 39, it came suppose 45. Okay, all are in mm. Okay, and while deloading, it is again 45, because from 2.5 itself we'll start deloading, and it came suppose 38, it came suppose 29, it came suppose 21, and it came suppose 16 mm. Okay, then we'll take the average of these two readings. Okay, so here one more column will be attached. So this is deflection average deflection will take. For example, here it is 16 and 14, so this will be 15 mm. Okay, so this is how we'll take the average of these two. Okay, so 5 different readings of deflection will be there, 5 different readings of loads will be there. Then we will find different 5 different modulus of rigidity. Here we'll find n1 equal to something will come, n2 equal to, n3 equal to, n4 equal to, n5 equal to something, and finally we will take the average of all those, which is n is equals to n1 plus n2 plus n3 plus n4 plus n5 divided by 5. That's it. So this is how we have to calculate the modulus of rigidity of this particular spring. Okay, so that's all.